Greetings, Calc 3 fans. Welcome to another video on sequences in series. This one to give us an introduction to series. In this video, I'll talk about some of the basics of series. I'll talk about how to determine convergence of a series, and then we'll talk about two special series, one called the geometric series and the other called the harmonic series. So as an introduction to series, I'll argue to you that as motivation, that fractions can be approximated by decimals. Right? We could say that 1/3 is approximately 0.33. It's also 0.333. It's also 0.3333. Or you could put 5 threes, and those are all approximations. And of course, if we had enough time, we could drop the approximation and write equals and just write threes forever. Okay, so that's to suggest that we can express 1/3 as a series, 0.3 plus 0.03 plus 0.003, and so on. Now, as a series, we can write this in terms of fractions also, right? 3/10 plus 3/100 plus 3/1000 plus 3/10,000, or the same as 3/10 plus 3/10 squared plus 3/10 cubed, and so on. Now, in summation notation form, this can be written as the sum from 1 to infinity of 3/10 to the I power. Okay, now to give you a little bit of a preview of what we're going to be doing with these types of series, we'll go ahead and think about the nth partial sum of this series. The nth partial sum means that instead of going out to infinity, we stop at n instead. So it would be something like, I'll call it S sub n. It's the sum from 1 to n instead of 3/10 to the I. So here, instead of being an infinite series, this would be a finite sum. So 3/10 plus 3/10 squared, 3/10 cubed, and so forth. But not going on forever in this case, stopping at 3/10 to the n power. Now, we can play around with this partial sum a little bit more, and if we do that, we'll look at a cool little trick here for the partial sum. So on one hand, I'll go ahead and write out some terms here. This nth partial sum is 3/10 plus 3/10 squared plus 3/10 cubed, all the way to 3/10 to the n power. Now, the trick here is that instead of looking at the nth partial sum, we'll go ahead and look at 1/10 times that nth partial sum. So I think you'll agree that 1/10 times that nth partial sum is 3/10 squared plus 3/10 cubed plus 3/10 to the fourth, and so forth. And this time, instead of the last term being 3/10 to the n, the last term is going to be 3/10 to the n plus 1. So now imagine taking the difference of these two. And I think you'll agree that if you take the difference of these two, s sub n minus 1/10 s sub n, that a whole bunch of these terms cancel. So I'm going to go ahead and write this out, and then I'll indicate which of the terms cancel. Okay, so you can see we've got here s sub n, which is 3/10 plus 3/10 squared plus 3/10 cubed, all the way out to 3/10 to the n power, minus 1/10 s sub n, which again is 3/10 squared plus 3/10 cubed, and so on, all the way out to 3/10 to the n plus 1 power. And I've tried to indicate for us the terms that cancel. So those terms that cancel are the squared terms, the cube terms. All of the other terms in the middle do too. The 10 to the n powers cancel. And then at the end of the day, we're actually just left with two terms here. And those two terms are exactly 3 over 10 and 3 over 10 to the n plus 1. Now, of course, if we have s sub n minus 1/10 s sub n, that quantity has to be 9/10 s sub n. So here's a formal expression for our nth partial sum, and we can do this every time. It tells us that s sub n is 9/10, oops, I'm sorry about that, 10/9 times the quantity 3/10 minus 3 over 10 to the n plus 1. So now ask yourself, what happens to that quantity as n goes to infinity? And I think you'll agree that as n goes to infinity, the term with the 10 to the n in the denominator goes to 0, and we're left with a finite expression for s sub n. So s sub n goes to 10/9 times 3/10, which I think you'll agree is exactly equal to 1/3. And that's what we expect to happen. And it so happens that this is exactly how we define convergence of any series. Okay, so here's the definition of the convergence of the infinite series, the sum I equals 1 to infinity of a sub I. We define s sub n to be the nth partial sum of that series. So you can imagine that we can always do this. We can always add up n numbers. Now we'll go ahead and formulate a sequence with these partial sums. So the sequence is the sequence s sub n, and if the sequence converges, then we say that the series does too. So this is exactly how we define convergence of a sequence. If the convergence of a series. If the sequence of partial sums converges, then the series does too. Okay, and this is a rigorous definition. If the sequence s sub n of partial sums, where those partial sums are defined by the sum from 1 to n of a sub I converges, then the series converges too. And we'll be using this definition to show that our two special series in this section are convergent or divergent, respectively. As an example, we'll go ahead and show that this series, 1, minus 1 plus 1, minus 1 plus 1, and so on, diverges. So to see that again, we'll go ahead and just look at the sequence of partial sums. So the first one is simple. I think you'll agree that the first one, s sub 1, is just 1. Now, s sub 2, of course, the sequence of the first two partial sums is 1 minus 1, which is 0. We can think about s sub 3 also. It's 1 minus 1 plus 1, which is 1. And I think you'll agree that s sub 4 is back to 0 again. So it's not quick to get a little bit bored with this, and we can see that the sequence of partial sums for this series is 1 if we take an odd number of sum in the sum, and 0 if we take an even number in the sum. Now, of course, this is a divergent sequence. We saw that last day. Right, it doesn't close in on a single number, so this series is 2. Okay, cool. So go ahead and wrap up this section talking about two special series. First, a discussion of the geometric series. Start with the definition. The series, the sum I equals 0 to infinity of a times r to the I power, which, as you can imagine, you can write as a times 1 plus r squared plus r cubed, and so on and so forth. This is called a geometric series with ratio r. Now, as a strategy for this series, I suggest trying to manipulate any geometric series till it's in this form. Okay, there are two reasons for this that we'll see soon. The first reason is that it's going to be easy to then identify what the ratio R is. And it turns out it's this ratio R that tells us whether the series converges. And second, it turns out also that a convergent geometric series is one in which we're able to find the sum. And it's going to be quick to identify the sum here as well. So here's an example. Let's go ahead and identify A and R for the following series. So for this first one, 1 plus 2 plus 4 plus 8, I think you'll agree that we can, that no manipulation is needed. So for this series, we can pretty clearly say that A is 1 and R is 2. The second series is similar, and it should be familiar to as the series that motivated this whole section when we were looking at the geometric interpretation of the area of that square. So here we've manipulated it until we can see pretty quickly that A is 1/2, and indeed R is also 1/2. The third one is similar but a little bit different. It turns out to be the series related to the repeating decimal 1/3. So for this third example, we can see pretty quickly that A is equal to 3/10 and R is equal to 1/10. Okay, so as we mentioned, it turns out to be the ratio R that tells us about convergence of this series. So to see that, we'll go ahead and note that the geometric series converges if and only if the ratio R is less than 1 in absolute value. And when it converges, we know its sum. Its sum turns out to be A over 1 minus R. So the proof of this is pretty quick, and it sort of mirrors the sequence of partial sums. So I won't go through it in detail. It was in a different video, but I'll go ahead and outline it. We'll first consider the cases where R is either plus or minus 1. And in the case where R is not 1, it turns out that we can express the sequence of partial sums S sub n just like we did before. And it turns out that that sequence of partial sums looks exactly like this. So we can solve this expression for S sub n just like we did with our 1/3 example. And we can see that the limit of this expression is finite if and only if R is less than 1 in absolute value. Of course, in that case, when R is less than 1 in absolute value, this term vanishes, and we're left exactly with A over 1 minus R. Okay, so that is the upshot of a geometric series, convergent if and only if the ratio R in absolute value is strictly less than 1. Okay, so a few examples exploring this. We'll determine whether the series converges, and if so, we'll find the sum. So again, here the key is to go ahead and express these series as in the manipulated form that we saw before. So for the first example, we saw that this can be expressed as 1 plus 2 plus 2 squared and so on. The ratio R is equal to 2, so this series diverges. That should make intuitive sense with what we know. If we start adding up numbers that get bigger and bigger and bigger, we'd expect that series to diverge. In the second case, we saw that the ratio R is 1/2, so it converges. And we know that it converges to A over 1, A times 1 over 1 minus R, so we get this value here, which of course is 1. Similar in the case of this last series, we saw that it can be manipulated into the form 3/10 times the quantity 1 plus 1/10 plus 1/10 squared, and so on. Of course, the R here is 1/10, that converges. And again, we know that it converges to 3/10, 1 over 1 minus 1/10. which is exactly 1/3. Okay, lots of geometric series can be expressed this way. All geometric series can, and it's quick to find their convergence. Okay, similarly, we sort of motivated this discussion with the discussion of a repeating decimal as an expression of a fraction, and it turns out that we can always change repeating decimals back into fractions too with geometric series. So we'll do that here, writing this repeating fraction with all fours as the following sum. Now it turns out that this sum we can express in fractions. This is exactly 4/10 plus 4/100 plus 4/1000 plus 4/10,000 and so on and so forth, which we can quickly turn into a geometric series. Now, of course, this is a geometric series with A equals 4/10 and R equals 1/10, so it converges. And it converges to the quantity 4/10 times 1 over 1 minus 1/10. Now that fraction simplifies pretty quickly. 4/10 times 1 over 9/10, which is exactly 4/9. So that's the fraction representation for the repeating decimal 0.444 forever. Okay, last thing to discuss in this section is an example of a series that's always divergent. The harmonic series is always divergent, as it turns out. So let me first tell you what that harmonic series is. The harmonic series is the sum, n equals 1 to infinity, of 1 over n. So 1 plus 1/2 plus 1/3 plus 1/4, and so on and so forth. So it's pretty quick to see that this is divergent. To see that this is divergent, we'll go ahead and look at a few partial sums of this series. So here I'll remind you that we'll express the nth partial sum, and I'm changing the index notation a little bit, no big deal, as the sum from k equals 1 to n of s sub k. So for instance, the second partial sum would be s sub 2. Similarly, the fourth partial sum can be expressed in the following way. The fourth partial sum is 1 plus 1/2 plus 1/3 plus 1/4. And the same thing for the eighth partial sum. And here, rather than writing out the first 4 terms of the eighth partial sum, I'm just writing it back in terms of s sub 4. Now there's a method to the madness here, and the method to the madness is the following. Should be quick for us to see that, for instance, s sub 2 is bigger than 1/2 plus 1/2, which is 2/2. Now similarly, s sub 4 can be expressed in terms of s sub 2. So s sub 4, it turns out, can be expressed as a number that's bigger than 3/2. Similarly, s sub 8 can be expressed as a similar inequality. Okay, so s sub 8 can be expressed as a quantity that's greater than 4/2. And you can keep going and come up with an expression for s over 2 to the n power, and it turns out to always be greater than n plus 1 over 2. Now, using a comparison test for sequences, we know that m plus 1 over 2 goes to infinity as n goes to infinity, so s sub n does too. So again, just a quick take-home message. The take-home message is that the harmonic series is divergent, and this is just one of the series that we know. It always diverges. Okay, folks, thanks for your attention today. Hope you enjoyed this video on an introduction to series in which we discussed 2 special series. We'll see you next time.